So welcome everybody. My name is T.V. Singh and I am Chief Computational Scientist at Office of Advanced Research Computing. And we have today Dr. Robert Fofrich. He will be speaking on challenges to mitigating climate change drivers and associated risks of surpassing lower emission targets. Let me introduce him to you. He was born in East Los Angeles and is an alumnus of West Los Angeles College. Currently, he is a UC President's Postdoctoral Fellow at the Institute of the Environment and Sustainability and works under the supervision of Dr. Elsa Ordway and Dr. Thomas Smith within the Department of Ecology and Evolution Biology. Before joining UCLA, Dr. Fofrich joined the Climate Impact Lab and was briefly a postdoctoral scholar in the Department of Earth and Planetary Sciences at Rutgers University. He received his Ph.D. in 2022 from Department of Earth System Science at the University of California, Irvine, where his research focused on energy and agricultural systems as they relate to climate change mitigation and adaptation. He has also served as a researcher at NASA JPL and Center for Environmental Biology in Orange County. And so without much ado, let's welcome Robert. And Robert, over to you.
Thank you, TV. Okay, let me just go ahead and share my screen. Okay, everybody. Thank you for joining me today. As TV said, my name is Dr. Fofrich Navarro, or just Dr. Fofrich for short. I'm a UC Presidential Postdoctoral Fellow, as well as a UCLA IDRE Postdoctoral Fellow. And here to talk to you about challenges to mitigating climate change, as well as some of the risks associated with surpassing lower emission targets. Since the industrial era, human activity has caused a shift in the global climate. On any given day, we as a species experience planetary average temperatures around 1 to 1.3 degrees higher than our ancestors did. And while this may not seem that high, we must remember that these numbers represent a global average, including the poles and the ocean. In fact, localized temperatures have risen more dramatically, resulting in increased frequency and intensity of extreme meteorological events. And while human activity has already shifted the planet's temperature, future temperature increases are not guaranteed. Instead, it is our collective actions and decisions that we make today that will influence whether we're able to stabilize our climate at current warming levels, or if we see global increases in temperatures in excess of 4 degrees Celsius. Over the past decade, there has been an increased efforts around the world aimed at limiting global temperatures at or below 2 degrees Celsius, including the adoption of the Paris Climate Accords in 2016. Nonetheless, there are numerous challenges associated in reaching these targets. And in this talk, I'm going to focus on a subset of these challenges, as well as talk about some of the risks associated with surpassing lower climate warming targets. My talk will therefore be divided into two major categories that highlight climate change mitigation challenges and risks. Within these sections, I will mostly focus on the electricity and agricultural sectors, given that these two industries are some of the greatest sources of anthropogenic greenhouse gas emissions. And in terms of agriculture, is also the largest driver of land use change. However, I will also be covering a relatively new area of research for me, and which I continue to develop, which is climate change attribution. That is, ascribing the effects of extreme meteorological events to human activity. The overall aim of this new work is to highlight populations which have been most impacted by historical climate warming, and similarly highlight which populations are most vulnerable to future climatic change. Before I get started, though, I would like to thank some of my collaborators from various institutions, as the work that you see here today couldn't be accomplished without them. I'd like to send a special thank you to my current postdoctoral advisor, Elsa Ordway here at UCLA, as well as my former PhD advisor, Steve Davis, who is now at Stanford University. And my other postdoctoral advisors, Robert Kopp and Kelly McCusker, who are at Rutgers University and Rhodium Group, as well as part of the Climate Impact Lab. Now, as some of you may know, climate change isn't a function of annual emissions, but rather the magnitude of climate warming is influenced by humanity's cumulative global greenhouse emissions. And while some greenhouse gases, such as methane, have relatively short lifespans in our atmosphere, the effects of carbon dioxide can last hundreds to thousands of years, meaning some of the carbon dioxide emitted by the first combustion engine is still affecting the climate system today. Nonetheless, future climate projections illustrate that stabilizing global temperatures at or below 2 degrees require significant and almost immediate reductions in anthropogenic emissions. For instance, if we look at this figure here, which projects a 1.5 degree climate pathway on the left and a 2 degree climate target on the right, we can see that the median emission projections show an immediate decrease after the year 2020, eventually reaching net zeros by mid-century, and then going down to what is known as negative emissions in the later half of the century, meaning we as a global society are absorbing more CO2 than we are emitting. This is followed by a plateauing of global temperatures and an eventual drawdown of temperatures to be in line with these climate targets. Now, historically, over 80% of carbon dioxide emissions have originated from the combustion of fossil carbon for energy, with slightly less than half of all carbon dioxide emissions being the direct result of fossil electricity generation. Therefore, in essence, climate change mitigation can be thought of as an energy transition problem. In fact, if we plot global CO2 emissions over time, and we overlay society's collective energy consumption around the world over the same time period, we can see that global carbon emissions correspond to society's total energy consumption. If we look closer, not only do we see that emissions and energy consumption rise together, but we can see that they peak and fall in the same years. If we take a closer look at the year-to-year change in emissions and energy usage over the last half century, this is highlighted by the green and red, respectively. Not only can we see the relationship between global CO2 emissions and energy usage, but we can also see huge dips in global emissions, which correspond to historical financial crises. For instance, the 1970s global recession, the 2008 financial crisis, and the COVID-19 global epidemic are all evident in the CO2 record. And this is because our economy takes massive amounts of energy to operate. From agriculture to manufacturing, we've industrialized almost every sector of our economy. Therefore, in order to reduce the potential for future warming, we must transition our society away from carbon dioxide emitting infrastructure. However, while climate change mitigation pathways require a swift transition away from carbon-based economy, things that produce CO2 directly, things such as power plants, factories, cars, and buses, tend to live long lives. For instance, the average coal burning power plant operates for around 40 years, while the average natural gas power plant operates from 35 to 37 years, and the average late model car in the US being around 13 years old. That means that some amount of our emissions budget is already claimed by things that we have already built and operate and expect to operate for years to come. Now, this brings me to this concept of committed emissions. Given that climate change is a function of cumulative emissions, we can simply ask if all existing and projected emitting infrastructure live out their expected lifetimes, how much CO2 will they produce, And what does this entail for climate change mitigation targets? Now, this question assumes no early retirement of this infrastructure or carbon capture and storage, which may be possible in some cases, but it helps us gauge the challenge. Using this concept, we can therefore forecast future annual emissions if this infrastructure operated for its intended lifetime. For instance, if we look at this rectangle here, this represents some piece of infrastructure that is coming online on a given year. Let's pretend that this is a power plant. Now, each one of these individual squares within this rectangle represents the total amount of emissions that we would expect this power plant to emit over its expected lifetime. We can also quantify the impact that these emissions will have on climate change pathways by calculating the expected cumulative emissions of newly deployed infrastructure and the effects that these emissions will have on various carbon budgets associated with different levels of climate warming. So in this example here, this rectangle, the green rectangle represents the same piece of infrastructure as the blue rectangle. However, instead of separating out the annual emissions over time, we simply assign all of the emissions that this power plant were to emit over its lifetime to the year it was constructed, as we already suspect that this is the total amount of emissions that this power plant will emit, and therefore we can subtract this from various carbon budgets associated with climate change mitigation targets. Additionally, we can utilize this concept to calculate how much energy generating capacity is coming online in a given year and forecast the future electricity generation potential from that infrastructure to project whether additional fossil power plants will need to come online to meet projected energy demand in coming decades. So in this top panel from this paper that we published in Earth Future in 2017, basically we assigned the total amount of energy generation potential to the year that the power plants came online. In the bottom panel, we are assigning it to the individual years over which we expect these power plants to operate from. And when we overlay projected energy demand, we can see whether the energy supply is enough to meet the demand and whether or not we suspect that more power plants will come online to meet this shortfall. Now, to better understand this concept, I designed this schematic in this paper that was published in ERL in 2020. Now, pretend that this black line represents a share of fossil electricity supply for a given climate change mitigation pathway. Now, the reason that this is decreasing over time instead of increasing over time as energy demand is projected to do is because this is the share of fossil electricity demand within the 1.5 or 2 degree climate change pathway, which show that we must wean ourselves off of fossil fuels. Now, we can then overlay existing power plant capacity. And in this example here, each one of these squares represents an individual power plant, and they are decommissioned over time based on the average lifetimes. We can see that in the first decade in this example, we have enough power supply to meet projected demand, but this quickly falls short in subsequent decades. Therefore, we expect additional power plants to come online, and in this case, fossil-fired power plants, to meet this shortfall, and this process to repeat itself. And so at some point, we have more fossil generating supply than we do demand for. But remember, overall demand is increasing. Therefore, we expect the utility operators to utilize this power over more renewable sources because of the electricity economics or the economics behind power utilities. And here you can see a simplified version of some of the results from our study, from the ERL study in 2020. Now, each one of these faint black lines are different projections of the maximum amount of CO2 emissions allowed from electricity generation, and in this case, in a 1.5 degree scenario for coal-fired power plants. The bold line is the median projection across all these different climate change scenarios. We then overlaid existing power plants and needed power plants to see if existing power plants would allow us to were in line with this different climate change mitigation pathway. And if we would have to retire these power plants prematurely, just how fast would we have to retire them, as this is something that climate models did not track or even program into their models. So when we let power plants operate for 60 years, we can see that we greatly overshot the scenario. Now, 60 years is a long lifetime, but it's not unheard of. In fact, here in the US, we have numerous power plants that operate for 60 years or more. So we continue to shorten the lifetimes to be more in line with historical norms. And we can see even with a 40-year power plant, which is the median age of a power plant around the world, we're still greatly overshooting the scenarios. So we continue to shorten the lifetime of existing power plants to see just how fast these things would have to retire in order to meet this 1.5 degree scenario. What we ended up seeing is even under unrealistically short power plant lifetimes, we were still overshooting the scenario. In fact, to meet a 1.5 degree scenario, coal-fired power plants would have to retire up to 3 decades earlier than they have historically. And under a 2 degree scenario, power generators would have to shut down in less than half the time that they have done so in the past. And while in some cases, retrofitting these power plants with existing carbon capture and storage technology is possible, these retrofits can be extremely costly and aren't always economical, as the cost can be in excess of building a brand new power plant. Now, a question that may come to mind is if we have less polluting technologies, such as natural gas power plants, why not simply retire more polluting plants for less polluting ones? Well, in this study that we published in 2020 in AGU Advances, we wanted to ask just that and investigate whether the natural gas boom that happened in the US in the early 2000s reduced the future CO2 commitments of the United States. What you're seeing here in this figure on the top part of this panel is the committed emissions, where we assign the total amount of emissions that we expect the power plant to produce to the year that the power plant was built. Now, the colors that you see on the top part of the panel just represent whether this is a coal-fired power plant in purple or a gas-fired power plant in orange. And the numbers here represent the total amount of committed emissions in gigatons. Now, the bottom part of this panel shows exactly the same thing as the top. However, we separated this into what we are calling realized emissions, or emissions that had already occurred in the year 2000, and separated out what were the emissions that were remaining in the year 2000. So in the year 2000, before the natural gas boom, we had 49 gigatons of CO2 remaining in the pipeline that would contribute to future climate warming. And in the year 2018, when we conducted this study, after the decommissioning of a substantial portion of the US coal fleet and the building of brand new, less polluting natural gas power plants, we had 43 gigatons of CO2 remaining. So what we ended up finding is while the natural gas boom did substantially reduce the annual emissions of the power sector, it did not substantially change the overall committed emissions from the US power sector, and instead locked us into 43 gigatons of emissions that would happen over decades to come. Another question that may come to mind is if renewable energy technologies exist, why don't we simply mandate that carbon emitting infrastructure retire immediately? Well, large changes to the operating conditions or prematurely retiring power generating infrastructure can be economically and politically risky. In the modern age, we've all become accustomed to reliable electricity. You all expect your computer to charge when you plug it in, or your food to stay cold when you put it in the refrigerator. Not to mention that in some cases, this is also a life or death situation. For example, if a hospital loses power, they do have generators to go for a few hours, but that puts all those patients' lives at risk. Um, this isn't the case around the world. There are still numerous countries and a sizable portion of the population that lack access to reliable energy. And this puts a lot of pressure on their society and also causes a lot of societal harm. Not only that, but power generating infrastructure is extremely expensive to build and operate. And instantaneously retiring all of these plants around the globe jeopardizes global financial stability. While exact estimates are largely proprietary and can range by generator type and location, in general, coal-fired power generators cost in excess of $1 billion per gigawatt, which is roughly enough power to supply about 750,000 American households, according to the US Energy Information Agency. And while climate mitigation pathways, which avoid more extreme climate warming, illustrate the need to close existing power plants before the economic lifetime has elapsed, recent power plant construction has shown an opposite trend, with new fossil generators being constructed around the globe, with the largest share of new coal and gas-fired power plants occurring in China and India. And this increases the financial risk associated with different climate change mitigation goals and jeopardizes these goals altogether. Therefore, in a subsequent study, we were interested in quantifying the monetary risk associated with prematurely retiring enough fossil generating capacity to achieve a 1.5 and 2-degree climate future, and highlight which corporate and government entities have the greatest financial exposures. Now, in this paper that's currently in review at Nature, we found that the current financial risk in the power sector alone to be 6.9 to $10.2 trillion under a 1.5 and 2-degree scenario. Now, to put these numbers into perspective, global GDP in 2022 was roughly $96 trillion. Therefore, this represents about 6 to 11% of annual global GDP. We also found that the largest share of monetary loss or stranded assets was in coal-fired power plants, followed by natural gas. And the countries with the largest financial risk to be China, the US, India, and Germany. However, the financial exposure from these different climate pathways is concentrated amongst few companies and is not spread evenly across different nations. Particularly, we found 5 state-owned mega conglomerate energy corporations in China and a state-owned company in India have a combined financial risk that exceeds $2 trillion for existing power infrastructure alone. This doesn't include power plants that are currently under construction or planned. Now, this is largely due to the fact that these power generating companies generally own a large number of younger power plants, which you can see here in the right panel. This is the years to retirement. So a lot of these highlighted in red and orange, you can see still have around 20 to 30 years or more left to operate. Additionally, we found that these same 6 companies are also responsible for the lion's share of total annual anthropogenic CO2 emissions, producing roughly a quarter of all emissions from humanity around the globe. And 100 companies emit about 75% of global emissions originate from the power sector alone. And this is highlighted by the black star here along the x-axis. Now, here are some of the names of some of these corporations that have the greatest share of financial exposure. What you can see here in this column is basically the country of origin, as well as if they were publicly traded, the stock market ticker symbol. Anything that you see with an asterisk next to the name indicates that this is a state-owned company with two asterisks indicating that it's a provincial state-owned company, not a national state-owned company. And while you do see China dominating this list, you also see a handful of Western publicly traded companies, such as RWE in Germany, NG Group in France, NL in Italy, as well as Duke Energy here in the US. The middle three columns will give you a sense of why these companies have such high financial exposures. You can see the total gigawatt capacity here on this column, as well as the number of generators that the companies own currently, and the average age of their power plant fleet here in this column. Lastly, in this very last column, you see the fuel mix of their power plants, with coal-fired power plants in red, gas-fired power plants in orange, and yellow representing oil-fired power plants, which are rare but not unheard of. Now, to recap this section, lower warming targets require the early retirement of fossil-fired infrastructure, in some cases 9 years after these power plants have been built. Replacing older, more polluting infrastructure with newer, less polluting infrastructure can lower annual emissions, but it can also unintentionally lock in similar levels of future emissions. And the majority of stranded assets under 1.5 degree target are owned by just 100 companies, with more than a quarter owned by 10 companies. Now, for the remainder of my talk, I'll be pivoting from climate change mitigation challenges to climate change risk. And I'll start by speaking on the climate change risk to global agriculture and agricultural-based climate change mitigation strategies. I'll end this section by speaking on a relatively new area of study for me, which is climate change attribution, that is looking at extreme meteorological changes which have already occurred and associating them with human-driven climate change. Now, the last portion on attribution is still very much under development. Nonetheless, I'm excited to present one of the novel data sets that we've developed for this project that can be used for future climate change attribution studies, as well as to highlight its potential to protect vulnerable populations around the globe. We'll start with the impacts of climate change on global agricultural production and future food security. Climate change is projected to substantially alter the average growing season temperatures and precipitation experienced in existing croplands around the globe. Now, in this figure, I am showing all the locations around the globe in which maize is cultivated on a quarter-degree grid. On the y-axis, you can see the total precipitation that maize experiences over its growing season. And on the x-axis, you see the average growing season temperatures. Now, the colors that you see here represent just how much maize or croplands are exposed to these climate conditions, with warmer colors representing a higher concentration of croplands being exposed to that same climate, and purple colors showing that very little is exposed to that climate. Now, generally speaking, with some exceptions, maize has historically not been grown in areas where the average growing season temperatures exceed 30 degrees. Again, there are some areas, as you can see here, the tail end, where maize is cultivated at higher temperatures, but generally speaking, the highest concentration happens on cooler temperatures than 30 degrees Celsius. What we ended up seeing in this study that's currently in review in ERL Climate is that under modest levels of warming, that is a 2-degree climate future, we actually see that the highest concentration of maize cultivation occurring at 29 and 30 degree Celsius, with a substantial portion of maize cultivation occurring at temperatures higher than 30 degrees. Now, this is concerning due to the fact that crop production rapidly decreases at higher temperatures. In fact, generally speaking, cereal crops, including maize, experience a 3 to 7% decrease in yield for every degree of warming above 29 degrees Celsius. This decrease in yield results in decreased profitability for the farmer and increased food prices. Therefore, in order to meet future food demand, farmers may be forced to abandon cultivation in existing croplands or switch out the crop variety that they choose to cultivate. While in some cases, farmers may adapt to future climatic changes by changing their farming practices or cultivation schedules. The potential for such in situ adaptations to offset climate impacts on a global scale is not clear. And it's also not as easy as it sounds, because in many regions, the timing of when you plant your crops is actually dictated by when precipitation may occur. In other cases, it has nothing to do with climate at all, but rather on when labor may be available, which has other economic factors that play into this. Therefore, future adaptation methods will depend upon both the efficacy of these adaptation efforts as well as the magnitude of future climate warming. For instance, in some cases, it may be possible for farmers to adapt to the regional cultivation to an additional degree of warming, but not 4 degrees. Now, this is particularly concerning at lower latitudes where future cropland temperatures are projected to exceed the maximum temperature conditions experienced by crops globally. If we use this figure as an example, we can see that maize production has historically occurred in any place where you see gray or colored shading. With the different colors, and now anywhere you see gray shading basically is a location in which maize has been cultivated in the past, and under a 2 degrees scenario, maize can continue to be cultivated there. At least it's unaffected by future climate warming. However, wherever you see this coloration are areas in which the future climate temperatures are too warm in order to grow maize. And the warmer colors, or just the coloration itself, shows by how much have we surpassed the maize growing thresholds. And what we can see here from this figure is even under a modest level of warming, that is a 2 degrees Celsius. Remember that this is what the world is working so hard in order to achieve, is a 2 degrees Celsius future. We can see that large areas of the tropics become uncultivatable for maize production using modern seed cultivars and farming practices. In fact, under a 2 degree climate future, the share of global maize and wheat cultivation or wheat production cultivated in regions where future climate is expected to exceed cultivation norms increases to just over 10% in both cases. Now, this results in greater food insecurity, and given that the human population and economic well-being is expected to increase during the same period, we can expect future cultivation regions to shift to areas with a more favorable climate to keep pace with demand and warming if other adaptive practices fail to mitigate the effects of climate change. And therefore, we may expect future climate future crop cultivation to shift forward as a result of this warming. In this figure here from the same paper, anywhere that, again, you see gray areas anywhere in gray or brown are areas in which wheat was cultivated historically, with gray areas meaning that under a 2 degree climate future, wheat is not affected under this future by the end of the century. Anywhere you see brown, however, are areas that wheat cultivation, the localized climate exceeds the need for wheat cultivation, and therefore we expect those areas to be abandoned, with the intensity of brown just showing how much yield is being abandoned. And the green areas are showing you the places with the nearest suitable climate to areas being abandoned. And so in this figure, you can kind of see a trend away from the poles towards, or away from the tropics towards the poles. And this becomes more evident as the planet warms further and further. And so I'll flip through these one more time so you can kind of see that trend. But we see things start to move away from the tropics. However, such large shifts to global agriculture would entail economic and food security losses for countries that are losing cropping areas. And these negative effects disproportionately impact developing countries in the global south while potentially benefiting more affluent nations at higher latitude. Now, in this figure, we can see an example of this using maize production. Now, anywhere that you see a bar is basically a country that is either gaining or losing production, with bar width indicating the share of that this production represents on a global scale. Bar height indicates how much this production is on a national scale, and bar orientation represents whether a country is losing production here on the left or gaining production here on the right. Finally, bar color indicates just how affluent or poor this country may be, with countries that are below the global mean shown in below the global mean per capita GDP shown in brown, and those that are more affluent shown in green. So in this figure, we can see that there's more brown shadings in countries that are losing production compared to countries that are gaining production. And when we took the average per capita GDP in countries that are losing production, we saw that it was about $4,500 compared to $26,000 in countries that were gaining production. And we saw this pattern repeat itself irrespective of what crop we analyzed in this study. And apart from the economic, food security, and national inequity implications that result from shifting global agriculture, there are also real threats to regional ecosystems that result from these spatial shifts in existing croplands. As of 2019, roughly half of all habitable land was already being used for food production. And while the vast majority of this land is being used for livestock, a quarter of which is still being used for crop cultivation. Therefore, we can expect that large-scale shifts in production would result in either further land use incursion or increased pressure on existing croplands that are unaffected by climate change. And while large areas of land are projected to become unfavorable for crop cultivation under different climate change pathways, climate change mitigation strategies also increase pressure on our global food system. This is because most climate change projections, which successfully avoid 2 degrees in future warming, do so by increasing the share of bioenergy production in order to increase or in order to lower atmospheric CO2 concentrations, as you can see here. So these are the results from some climate models where you see bioenergy production increasing over the next century. And at the same time, this results in atmospheric CO2 concentrations plateauing by mid-century and finally dropping down at the end of the century. Now, this entails switching large areas of land from producing food to growing crops that can be converted to liquefied fuels or burnt for energy directly, and capturing and storing the associated CO2 before it escapes to the atmosphere, thereby creating an influx of CO2 from the atmosphere to the biosphere and ultimately storing this CO2 in carbon or in geologic formations deep under the ground in a process known as negative emission. In fact, bioenergy and other negative emission processes are critical in achieving lower warming scenarios, as most climate models struggle to stabilize future temperatures at or below lower climate targets. In many cases, these same models overshoot the climate targets in the short term and utilize negative emission processes to reduce the end of the century CO2 concentrations back in line with lower warming targets. However, there are large disagreements between climate models on how much negative emissions is necessary to stabilize future temperatures at or below 2 degrees Celsius. Nonetheless, a large part of this uncertainty is associated with our collective action today and just how fast we as a society are able to decarbonize. The longer the action is delayed, the greater the negative emissions requirements will be. Decarbonization delay also results in higher overshoot, which can jeopardize biologically based negative emission pathways due to climatic thresholds associated with different plants and the regional heterogeneity in projected warming. For instance, in this study that is almost ready for submission, we are interested in testing the feasibility and ecological trade-off of cultivating different crops that can be used for bioenergy in the tropics. We found that around 45% of oil palm, soybean, and sugarcane grown in the tropics were cultivated in areas with an unfavorable climate by mid-century. Now, this is concerning given that many biologically based climate mitigation solutions rely on tropical regions to stabilize future temperatures. We also observed that in many cases, localized temperatures and precipitation exceed the necessary climatic conditions for crop cultivation within decades in a 2-degree climate scenario, and by mid-century in a 1.5-degree pathway. Thus, in many cases, biologically based negative emission processes must occur in locations outside the tropics, which can have many negative implications for higher latitudinal ecosystems and climate change mitigation efforts. Now, for the remaining of my time, I want to discuss some ongoing work that focuses on climate change attribution. However, much of what I'll be discussing here is a novel and robust data set that my colleagues and I at the Climate Impact Lab have developed for future climate change attribution research with the intentions of answering these questions. How much has the human exposure to extreme weather events changed due to climate warming, and how has this affected human mortality? Which populations are been the most vulnerable to climate warming changes, and what can we infer about future risks? Now, while there is increasing evidence ascribing recent climate warming to rising greenhouse gas emissions, attributing a single meteorological event to human activity involves quantifying the likelihood of an event with and without anthropogenic forcing. Now, this has been much more challenging to do due to the limited meteorological records, which are often shorter than the natural cycles of these extreme events. Therefore, while the news likes to associate many meteorological extremes with climate change, it is highly inaccurate to do so. Instead, tying these events to human-driven climate change involves analyzing climate model simulations, which replicate the historical climate and the effects of anthropogenic forcing on the planetary system, and compare these results with climate models that omit anthropogenic climate warming. However, although existing attribution studies do provide useful insights, they rely on existing global climate models, which suffer from key limitations and implicit biases, such as lacking the spatial and temporal resolution for regional analysis, simplified climate processes, and the irreproducibility of historical meteorological events, which limit their ability to inform researchers and the public. Therefore, we developed a new data set covering daily average global temperatures over the past 4 decades without the influence of human activity on the climate system, which is based on the observational record obtained from the 5th generation European Center for Medium Range Weather Forecast atmospheric reanalysis of the global climate, or more simply put, ERA5. Now, while our methodological approach is quite computationally expensive and complicated, in summary, it involves incorporating global historical and historical natural temperature projections from the couple model intercomparison project in order to quantify the effects of anthropogenic forcing on the past climatology and apply these differences to daily ERA5 temperature values on a quantile basis for each location and for each day. We then test whether or not the adjustment differences being applied to ERA5 are proportional to the temperature differences observed in the historical and historical natural global climate model simulations, and demonstrate that the temperature adjustments increase in years with greater magnitude of anthropogenic warming. That is, increasing in years that are more close to the modern age. In all cases, we observe the greatest temperature adjustments occurring near the poles, which is consistent with observed trends of anthropogenic climate warming. Additionally, in specific global climate models and for particular years, we detect cooling effects in certain regions, indicating that the historical global climate model predicts cooler temperatures than the corresponding climate models which omit anthropogenic forcing on the climate system for those areas. Nonetheless, these cooling patterns may vary from one global climate model to another due to internal model physics and the response to external forcing, such as those from human source aerosols. And as such, these variations are not unexpected or unique to our results. Now, here you can see some of the results from our data set. On the left, you're seeing the outputs from global climate models with the historical climate model shown in orange, and the one that removed humans from impacting the Earth system shown here in blue. The observational record is shown here. And so this is the actual temperature record from 2008 to 2010, averaged around the globe. And our data set is shown here in purple. Now, our data set involves, is created through many global climate models, but you can kind of see that the difference between our data set and the observational record is roughly proportional to the difference between the historical and historical natural climate simulations. However, if you look closely, you'll see that our data set, the daily and interannual variability of our data set does not follow the global climate models. Instead, it follows closely to the observational record, meaning that we're able to successfully remove the spatial and temporal biases from the global climate models, which aren't correct anyways, but keep the relative contribution of human-driven climate warming and remove that from the observational record. Here you're seeing another example of our data set, and where you can clearly see the resolution has been greatly improved compared to the global climate model output. On the left, you're seeing an output of one of the global climate models, which has a resolution of about 100 to 500 kilometers at the equator, meaning when you're trying to do regional studies, you really can't do much with that type of resolution. On the right, you will see our data set, which has a 25-kilometer resolution at the equator, which follows the native resolution of the observational record of ERA5. And here I'm just showing a quick example of how our data set can contribute to climate change attribution research. Our data set is unique because it enables us to examine a specific year and a specific day of the year and envision what the weather might have been like if anthropogenic climate change weren't happening. Additionally, we can analyze the climatological record consisting of 20 to 40 years of meteorological data to quantify differences in extreme events, such as those seen in heat waves. And here I'm illustrating, for example, the number of days in which daily average temperatures exceeded 30 degrees in the historical record and our data set beating that. What we found is that in many of the world's hot regions, that is like the Sahara Desert, the Arabian Peninsula, the Indian subcontinent, or Australia, there has been an increase in the frequency of the number of days which temperatures reach 30 degrees Celsius. And in some areas, more than 200 additional days with these temperatures can be attributed directly to human-driven climate warming. The next stage of this analysis includes quantifying the relative contribution of human-driven climate change on human mortality from extreme temperature events, such as the heat waves, which have occurred a few years ago in the greater Seattle area and across Europe. Now, this entails running our data through temperature mortality response functions and comparing the results to those generated using the historical climate. Additionally, I'm leading a separate analysis that looks at pronounced extreme meteorological events that have occurred over the past 4 decades and quantifies the likelihood that these events would have occurred without human influence on the climate system to describe which areas have been most affected by human-driven climate change. And just to quickly summarize this last portion, crop production may need to shift forward in response to future climate warming if other adaptive measures fail to keep pace with climate change. Overshooting lower warming targets jeopardizes tropical bioenergy negative emission solutions. And anthropogenic climate warming has already substantially increased the number of hot days at lower latitudes, in some cases by as much as 200 days. And with that, I'd like to thank you and take any questions. Thanks again.
Yeah, Robert, any questions? You can just unmute yourself and ask the questions directly. Any question? Okay. Yeah, there is one in the chat.
Oh, the chat wasn't a question, it's just a comment.
Not, I have a question on, you showed this 2008 and 1970 depression on the financial thing.
Yes.
And that's interesting to see. Was it a result of the just because what I feel is, or my gut feeling is that when depression is there, these big energy producer like plants, they don't stop working. What could be the reason?
Yes, that is correct. Usually they do work at less intensity because the economy is what's driving energy consumption. And so when the economy slows down, like for example, we as just normal consumers at home, we are not a substantial portion of the energy consumption. But factories, things like that consume a lot more energy than we do. And so when those portions start to slow down, the power plant may be still operating, but it's not operating at the same intensity because power isn't something that we can store on large scales. Like there are ways that we can store some electricity through batteries, and also when there's or like using a reservoir, a water reservoir as a big battery. They sometimes pump water uphill when there's power, and then when there's no power, you utilize that water to then run a hydro turbine. But in general, power has to be consumed as soon as it's generated. And so in times where you don't need as much electricity, you ramp down the power plants. And certain power plants are easier to ramp down than others. Coal-fired power plants are typically more challenging to stop and start. So typically they will be the last ones to be stopped, but a gas-fired power plant, the more advanced ones can operate in a similar way as your car. You just turn them on and turn them off, and there's not really a huge repercussion. So because of that, when in general society is not using as much electricity, power plants don't get decommissioned, but they get mothballed and just kind of sit there idle.
Okay. Great. This was a great presentation. And if there is no more questions, let's thank you to and thanks to Robert, and hope you
Thank
have.
you all for
Thank you so much.
Yeah, thank you all for
Such
joining.
an important, most important topic. Thank you.
Hope you have a great rest of the day. Thank you. Thank you, Robert.
Thanks, TV. Bye.